In today's video, we are going to discuss the analysis of crystal structure, X-ray analysis of sodium chloride. Okay. How to find out the crystal structure of sodium chloride by X-ray diffraction technique. Okay. However, the discussion is highly non-mathematical. We are not going into rigorous mathematics that is involved. So this is a very simple application of Bragg's law in determination of crystal structure. The apparatus or the method that is used to find out the crystal structure of any compound out of several methods, one of the prominent method is called as rotating crystal method. This is one of the widely used method for determining the crystal structure. As the name suggests, here the crystal that is mounted is rotated and it is exposed to X-rays at various angles. The apparatus or the instrument or the setup that is used to study the crystal structure of sodium chloride is called as X-ray diffractometer, or sometimes also called as X-ray spectrometer, which is shown in this figure. What does this contain? It contains a tube which is called as X-ray tube. Let us not go into details of the components present in the X-ray tube. So this X-ray tube emits X-rays. That is what we should know now. The X-ray tube contains a metal target which is mainly, most of the time, made up of either copper or molybdenum. When high voltage is applied across the metal target, X-rays are generated. Let us not go into the mechanism of how these X-rays are generated. So highly energetic X-rays of particular wavelengths are generated. These monochromatic X-rays then passes through a focusing slit. What does this focusing slit do? This focusing slit focuses the X-rays, so we get a very narrow beam. Beam of X-rays, and this highly energetic narrow beam of X-rays falls on a crystal which is called as a single crystal, which is represented by C. In our particular example, this single crystal is of sodium chloride. So I have kept a sodium chloride crystal on a table which can be rotated. Therefore this table is called as turntable. Now in this still diagram, one of the HKL plane is exposed to X-rays at a particular angle theta. So what we do now is we rotate this turntable, such that the crystal is exposed to the X-rays at various angles. At those angles, the X-rays are diffracted and the intensity of the diffracted X-rays are collected in this recorder, which may be even a detector. Now, based on Bragg's law, that is n lambda is equal to 2d sin theta, at some angle theta we can observe a bright spot in the recorder or the detector, and where this Bragg's angle or Bragg's equation is not satisfied, nothing is recorded in the diffractometer. So once this crystal is rotated at different angles, at some angles Bragg's equation is satisfied and we observe a bright spot, and at some angle Bragg's equation is not satisfied and we do not get a bright spot. So we rotate the crystals in various possible orientations so that different HKL planes are exposed to X-rays at various angles. So the resultant, okay, if I have a detector somewhere here. So you get a diffraction pattern which contains a series of spots. So what I have shown here are the bright spots that are observed in the diffraction pattern. And why do this bright spot arises? Each of this bright spot arises because at a particular angle this Bragg's equation is satisfied. N lambda is equal to 2 theta is satisfied. For example, this bright spot is because of the satisfaction of Bragg's law. N lambda is equal to 2 d psi theta for some HKL planes. Here we don't observe anything. What does it mean? This corresponds to an angle theta which does not satisfy Bragg's equation. N lambda is equal to 2 d psi theta, and therefore no bright spot is observed here. Okay, so this is the characteristic diffraction pattern containing series of spots distributed in a very regular manner. So the way these spots are arranged in space is very characteristic of the sample. Now we have to analyze two things from the diffraction pattern. One is the angle theta, which satisfies Bragg's equation, or this angle theta is nothing but Bragg's angle. So from the experiment we have to find two data. One is the Bragg's angle corresponding to maximum reflection. The second data we require is the intensity of each of these bright spot. So I'll repeat, two data are obtained from an X-ray diffractometer. One is the angle theta, which is Bragg's angle corresponding to maximum reflection. The second data that is obtained is intensity of each spot on the diffraction pattern. And these two data are very helpful in finding out the crystal structure. In this case, the crystal structure of sodium chloride. Okay, let us not go into much experimental details. Let us use some data that is obtained from this experiment. I have copied down the data. Yes, here in this table I have given a list of Bragg's angle theta corresponding to maximum reflection from three planes: 100 plane, 110 plane, and 111 plane. Okay, I have not considered other planes because these planes are primary planes from which maximum intensity is observed. Okay, so I am only considering these three planes. And here I have given the Bragg's angle theta corresponding to first order reflection, second order reflection, and third order reflection from all of these planes. So 5.9 degree corresponds to a first order reflection from a 100 plane. 8.4 degree corresponds to a first order reflection from 110 plane. Similarly, 5.2 degree corresponds to a first order reflection from a 111 plane. Similarly, 11.9, 17.0, 10.5 corresponds to second order reflection from 100, 110 and 111 plane. 18.2 degree corresponds to third order reflection from 100 plane. However, the third order reflection from 110 and 111 planes are very weak and they are not almost detected. And also simultaneously the calculated values of sine theta is given in the next column. Okay, so sine 5.9 is 0.103. Similarly, sine 8.4, sine 5.2, all the sine theta values are calculated. Now the purpose of calculating sine theta is because in our previous video we have discussed a very important relation, and I told you this relation will be helpful in the coming classes. Okay, the relation that we have discussed in the previous video is the ratio of the interplanar spacing is equal to the ratio of the reciprocal of sine theta corresponding to those planes. That is d100 is to d110 is to d111 is equal to reciprocal of sine theta 100 is to reciprocal of sine theta 110 is to reciprocal of sine theta 111. As we already know the values of sine theta, say for example if we consider the first order reflection, okay, so 1 by sine theta is 0.103 is to 1 by 0.146 is to 1 by 0.0906. If you work this out, this ratio is 1 is to 0.705 is to 1.14. And I had given another table, okay, from which we can find out the standard values of the ratios D100 is to D110 is to D111, and this ratio is almost equal to the ratio that is generally observed for an FCC lattice. So from this we can conclude that therefore sodium chloride belongs to face centered cubic lattice. So this conclusion is drawn based on 2 theta values or theta values. So the position of the diffraction spot gives us information about the type of crystal lattice. Okay, if I refer back to the diagram of X-ray diffractometer, this is the diffraction spot. So the position where a diffraction spot occurs, so if we analyze all these positions, that is nothing but the angle theta, it gives an information about the type of lattice. In this example, sodium chloride belongs to FCC lattice. Okay, but if I want to get a very detailed arrangement of sodium and chloride ions in the crystal, we have to go much into the details. Okay, for that we require the intensity of each of the spot, not just position, we also need the intensity of each of this diffraction spot, and the intensities of these spots are listed in this table number 2. Okay, down the column you have order of reflection: first order, second order, third order, fourth order, and fifth order reflection, and the intensity of the X-rays reflected from an 100 plane, 110 plane, and 111 plane, corresponding to first order up to fifth order reflection. These, all of these are relative values. If the reflection, first order reflection from 100 plane is given an value of 100, intensity is taken as 100, then the relative value corresponding to reflection, second order reflection from an 100 plane is 19.9, third order reflection is 4.87, fourth order reflection is 0.79, fifth order reflection is 0.12. Similarly, you have the intensities of the X-rays reflected from 110 plane corresponding to first order, second order, third order. We don't have data for fourth and fifth order. Similarly, the last column gives the intensity of the spots corresponding to first order up to fifth order reflection for a 111 plane. To analyze this data, we should know that the intensity of the diffraction spot depends on 2 factors. One is the intensity is directly proportional to mass of the structural unit. Okay, I am using a rather a very simple word. Okay, actually intensity is directly proportional to a term which is called as scattering factor. Let us not go into that much detail. So in a very simple way, you can say that intensity is directly proportional to the mass of the structural unit. Okay, what does it mean? In sodium chloride you have two entities, structural units. One is sodium plus ion and chloride ion, and these particles don't have same mass. Chloride ion is heavier compared to Na plus. So from this we can observe that the intensity of the X-rays reflected by a plane containing chloride ions must be greater than the intensity of X-rays reflected by a plane containing sodium ions, because mass of chloride is greater than mass of sodium. The second thing we have to observe is intensity of X-rays reflected from a plane is inversely proportional to order of reflection. What does it mean? As the value of n increases, as the order of reflection increases, intensity decreases. Okay, so based on these two, that is order of reflection and mass of the structural unit, it is possible to analyze the intensity of each spot. Now let us consider the reflection from 100 plane. Okay, here we have the reflection from 100 plane. What we observe is, as we go down the column, as the order of reflection increases, n increases, the intensity decreases uniformly. Okay, there is a decrease in intensity. So here we observe this relation holds good. Intensity is inversely proportional to 1 by n, because as n increases down the column, intensity decreases. So what does it suggest? That the 100 planes in sodium chloride, each of the 100 plane must be made up of uh, similar arrangement of atoms or ions. I repeat, in this column corresponding to 100 plane, what we observe is, down the column, as the value of n increases, I decreases. So what does this suggest is, each of the 100 plane of sodium chloride crystal contains a similar arrangement of ions. Okay, for example, this is just an example I am giving. This is a 100 plane. So if you have an arrangement something like this in the 100 plane, this is the arrangement of ions in a 100 plane. If I consider the next 100 plane, the next 100 plane should also contain same arrangement of ions. So if I add up the mass of all the atoms present in one 100 plane and the other 100 plane, they are same. So mass has the same effect on the intensity. Whether it is this plane or this plane, the mass is same. So the effect of mass on the intensity is same in both the planes. So the intensity now depends only on n. Therefore, from this data, we are able to conclude that each of the 100 plane in sodium chloride consists of same arrangement of ions. Now let us look at 110 plane. Similar trend is observed in 110 plane also. When we move down the column, n increases, whereas intensity decreases. Intensity decreases. So I is again inversely proportional to n. This equation holds good. So what does this suggest? This also suggests that, similar to 100 planes, all the 110 planes in sodium chloride contains a similar type of arrangement of particles. Now let us focus on 111 plane. This is interesting. Here we observe that the intensity of the first order reflection is 9. The intensity of the second order reflection should have been less, but it is greater than the first order reflection. Again, if you go to third order reflection, the intensity of the third order reflection is less than the second order reflection. This is acceptable. Whereas if I go to fourth order reflection, again the intensity of the fourth order reflection is greater than the third order reflection. So what we are observing is, the intensity is varying alternatively. It is increasing, decreasing, increasing, decreasing. So here I proportional to n is not observed. Okay, is not observed because it is not varying uniformly. As n increases, I should decrease, but here what we are observing is, there is an alternative variation of intensity. It increases and next decreases, again it increases, again it decreases. So here what does it indicate? The intensity of the X-rays reflected from these planes not only depends on order of reflection, it also depends on the mass of the structural unit, in such a way that, if I consider two 100 planes, sorry, 111 planes in sodium chloride, the arrangement of atoms in one 111 plane is different from the arrangement of atoms in the other plane. Okay, so we can give different possibilities. I will stick on to one possibility which is actually the correct possibility. So here, one of the 111 plane I have shown ions by red color. In another 111 plane I have shown ions made up of blue color. So what does this indicate is, one of the 111 plane contains arrangement of sodium ions, the other 111 plane, that is the adjacent 111 plane, contains only chloride ions. So the total mass, if I count the mass of all the atoms in this plane, is different from the mass of all the atoms in the 111 plane. So the intensity of the X-rays reflected from this 111 plane is different from the intensity of the X-rays reflected from the second 111 plane. So this may be the possible reason for variation of intensity for 111 plane. Let me give a more diagrammatic explanation. So here I have given, so you have 111 plane. This is one of the 111 plane which contains only chloride ions. So I have labeled it as chloride plane. The next 111 plane, that is also made up of only chloride ions. That is why it is called as chloride plane. And in between these two chloride planes, exactly at half the distance, you have another 111 plane which is purely made up of sodium ions. So it is called as a sodium plane. So if I consider the first and the third plane, it contains only chloride ions, and since chloride ions are having greater mass than sodium ions, the intensity of the X-rays reflected from a chloride plane is greater than the intensity of the X-rays reflected from a plane containing sodium ions. Okay, so let me consider a first order reflection from these two chloride planes. Okay, I am considering a first order reflection from these two chloride planes. So you have X-rays falling and getting reflected from the first chloride plane. Similarly, you have X-rays falling on the second chloride plane and getting reflected. So to observe first order reflection, what should happen? The X-rays reflected from these two chloride planes should undergo constructive interference. And to observe constructive interference, the condition is path difference between these two beams should be equal to n lambda. And here, since we are considering first order reflection, n is equal to 1. So the path difference should be equal to lambda. But here, in addition to the X-rays reflected from the two chloride planes, you have X-rays falling even on a chloride plane which is reflected. Okay, and the X-rays reflected by sodium plane, it superimposes with the X-rays reflected by the chloride planes. Now the distance between these two chloride plane is d. The distance between these two chloride plane is d. So what is the distance between the chloride and the sodium plane? It should be d by 2. Similarly, the distance between these two planes should also be equal to d by 2. Now the setting is such that you are observing a first order reflection from these two chloride planes. It means the path difference is lambda when the distance of separation is d. So what should be the path difference between the chloride plane reflected X-rays and sodium plane reflected X-rays? It should be lambda by 2 because you have reduced the distance by d by 2. So the path length will also be reduced by d by 2. So the path difference between the X-rays reflected by a chloride plane and the X-rays reflected by sodium plane will be lambda by 2, and the path difference is equal to lambda by 2 is a condition for destructive interference. So what is happening here? X-rays reflected from chloride plane are undergoing constructive interference, but the X-rays reflected from a sodium plane which is out of phase results in destructive interference. And please remember that the X-rays reflected from chloride are having greater intense than X-rays reflected from sodium plane because they are having greater mass. So let me write a diagram here. So this is the X-rays reflected from the first chloride plane. This is the X-rays reflected from the second chloride plane, which are in phase and they go constructive interference. But the X-rays reflected from sodium plane, they are out of phase and their intensity, that is amplitude, is slightly less than the chloride. So if I mix these three, what will happen is they will result in a X-ray beam which is having slightly lesser intensity than the result of adding these two beams. So now ಎಷ್ಟು intensity chloride plane ಇಂದ ರಿಫ್ಲೆಕ್ಟ್ ಆಗಿರುತ್ತೆ X-rays ಇಂದ ಎಕ್ಸ್ಪೆಕ್ಟ್ ಮಾಡ್ತಿದ್ದೇವೆ ಅಷ್ಟು ಇಂಟೆನ್ಸಿಟಿ ಮೆಜರ್ ಮಾಡಲ್ಲ, ಇಂಟೆನ್ಸಿಟಿ ವಿಲ್ ಬಿ ಲೆಸ್. ಯಾಕಂದ್ರೆ ಎರಡು ಕ್ಲೋರೈಡ್ ಪ್ಲೇನ್ ಇಂದ ರಿಫ್ಲೆಕ್ಟ್ ಆಗಿರುತ್ತೆ X-rays ಕನ್ಸ್ಟ್ರಕ್ಟಿವ್ ಇಂಟರ್ಫರೆನ್ಸ್ ಆಗಿ ಬ್ರೈಟ್ ಸ್ಪಾಟ್ ಕೊಟ್ಟರು ಕೂಡ ಅದರ ಇಂಟೆನ್ಸಿಟಿ ರೆಡ್ಯೂಸ್ ಆಗಿರ್ತದೆ. ಯಾಕಂದ್ರೆ these planes, okay, these X-ray beams undergo destructive interference from the beams that are reflected by the sodium plane. So the net intensity ಏನಾಗಿರ್ತದೆ decrease ಆಗಿರ್ತದೆ. Okay, so that is the reason why the first order reflection in the 111 plane, the intensity of the first order reflection is less, whereas the intensity of the second order reflection is much greater. Actually, as the order increases, intensity should decrease, but intensity here has increased. How can you possibly explain? For that I have shown a second order reflection here. Again you have three set of planes. This is the chloride plane, first chloride plane, this is the second chloride plane. So X-rays are reflected from both of these planes at a particular angle, and to observe a second order reflection, the path difference between these two planes should be equal to 2 lambda. But simultaneously the X-rays fall on the sodium plane and are reflected, and since the distance between two chloride planes is d, this distance is half of d, this distance is also half of d. So what does it mean? That the path difference between the beams reflected by X-rays and beams reflected by sodium ions is lambda. This is also lambda, and lambda is again a condition for constructive interference. So the X-rays reflected from chloride planes are in phase and the X-rays reflected from the sodium ion plane is also in phase. So all the three waves are in phase with each other. Okay, so these are the X-rays reflected from the two chloride planes, and this is the X-ray reflected from a sodium plane, and all these three are in phase with each other because the path difference between these two is 2 lambda, and the path between these two, or the first and the last, is lambda. So all are in phase with each other. So on adding, they give a very bright spot resulting in constructive interference. So that is the reason the second order reflection is, okay, unusually having very high intensity compared to first order reflection. So in this way, based on the intensity data, it is possible to predict the arrangement of particles, not only the arrangement, also to predict the nature of the particles present in each of the lattice plane. So based on all these arguments, the proposed crystal structure of sodium chloride is given in the diagram, and this is FCC structure. Okay, so the sodium chloride structure is also called as rock salt structure. Okay, it is face centered cubic. You can see here at the center of each faces you have a ion. In this particular example, I have taken sodium ion at the center of each face, and you can see here you have an alternative arrangement of sodium ion and chloride ion. Sodium ions are shown by small circles, whereas chloride ions are shown by larger circle. This is because size of chloride is greater than size of sodium ion, and the coordination number, that is the number of ions of one type surrounding the other ions in the crystal lattice, which is called as coordination number, for chloride is 6. Coordination number for sodium is also equal to 6. Okay, let us see here. If I take the central chloride ion and count the number of sodium ions, you have 1, 2, 3, 4, 5, 6. So you have 6 neighboring chloride sodium ions. Okay, so this is a very simple structure of rock salt or sodium chloride. Please practice the diagram. Okay, uh, let me try to draw this structure so that it will help you to practice. Okay, how to draw the structure. Let me try. So first you have to draw a single large cube. Okay, since I'm not using any scale, it may not be the perfect diagram. Okay, you have to use scale to draw the structure. So first you have to draw a cube, then you have to divide this cube into 8 small cubes. So divide each face into 4 squares. Okay, so one face is divided into 4 square. This surface is also divided into 4 square. This surface is also divided into 4 square. This is also divided into 4 square. Now the front face is also divided into 4 square. The back face is also divided into 4 square, and an additional square that is formed at the center, that should also be divided into 4 squares. So altogether a single large cube is divided into 8 cubes. Now you have to place the correct ions at correct lattice points. Okay, as I already told you, it is an alternative arrangement of sodium and chloride ion. So if you have a sodium ion here, here should be a chloride ion. Okay, I will represent chloride ion by a different color. So let me first complete filling sodium ion. So again there should be a sodium ion here. Here alternatively there should be a chloride. Here again it should be sodium. Here you should have chloride. Here should have sodium. Okay, here again you have chloride. Okay, and when there are 4 sodium ions in the corner, we have to place a sodium ion at the center of the face. Similarly, here you have sodium, here also you have sodium. Okay, here you have sodium, and at the center you have sodium. Again at the center you have sodium. Okay, this is also the center. You should have sodium on the at the center of all the 6 faces. So this represents sodium ion. Let us represent chloride. Here you have a chloride, chloride, chloride. So alternatively you have one sodium and one chloride. Okay, so the larger ion, in which case, in this case I have used green color to indicate chloride ion. Okay, so it is easy to draw the crystal structure of sodium chloride. However, you require to practice drawing this structure. So this is how, in a very simple non-mathematical way, I have tried to explain the determination of crystal structure of sodium chloride from X-ray diffraction measurement. So with this I conclude today's video, and I have covered a major portion of the syllabus related to solids. Thank you.